Foundational programming assumes the program fits, that you can document the rooms, calculate the gross area, and hand the package to schematic design. Advanced programming is what happens when the rooms don't fit, the budget doesn't fit, or the stakeholders don't agree. A campus client wants 9 buildings on a site that supports 6. The hospital wants single-bed rooms, but the operating budget is sized for semi-private. 3 department heads want adjacency to the same atrium. The ARE writes advanced programming questions from those collisions, and an architect who picks the wrong trade-off here can be sued by the owner when the building can't be operated within budget, or face AIA disciplinary review for signing a program the firm knew would not perform. The architect's job is no longer to gather. It is to recommend, with documented trade-offs, the version of the program the owner can actually afford to build, finance, and operate. Here are the 4 reasons these topics sit on the advanced side of the division. 4 reasons these programming topics are the advanced half of the division. First, campus, phased, and mixed-use programming is no longer a single program. It is a sequence of programs across parcels and across years, where each phase has to leave the site able to operate while the next phase is built. Second, cost analysis goes long. You are not just benchmarking first cost per square foot. You are running lifecycle cost analysis over a 30-year horizon and using value analysis to compare alternative ways of delivering the same function. Third, facility-type programming carries hidden rules. Healthcare has clearance, infection control, and licensing-driven program logic. Education has prototype standards. Office and residential each have efficiency benchmarks and tenant build-out assumptions. Generalists who miss the type-specific rules write programs that fail at code review. And fourth, when the owner has multiple candidate sites or multiple program strategies, the architect produces a weighted scoring matrix the owner's board can defend in a public meeting. Here is the chronological roadmap across 5 advanced subsections. Walking the advanced module in order. 4.1 tackles complex program forms, multi-building campuses, phased developments that have to stay operational mid-construction, and mixed-use programs where the residential, retail, and office stacks have to share a single envelope. 4.2 is the cost stack, cost benchmarking during programming, lifecycle cost analysis over 30 years, and value analysis to compare functionally equivalent alternatives. 4.3 goes deep on facility types, healthcare programming, educational facility programming, and office and residential programming, each with its own embedded code rules. 4.4 handles people, power interest grids for prioritizing stakeholders, managing large stakeholder groups, and using post-occupancy evaluation and evidence-based design to bring data into the room. And 4.5 closes with site selection, weighted scoring criteria, financial feasibility, regulatory feasibility, decision matrices, and the multi-criteria analysis that produces a defensible recommendation. One posture shift before we step into section 4.1. 4 things to hold in mind through this advanced module. First, every recommendation here commits owner capital for decades. Treat the work as capital risk management. The architect is signing a piece of the owner's long-term balance sheet. Second, when a question presents multiple stakeholders with conflicting priorities, read it as a prioritization problem solved with weighted criteria, not a consensus problem solved by compromise. Compromise produces buildings that satisfy nobody. Third, watch the framing on cost questions. The exam often presents a first cost answer next to a life cycle cost answer, and the right call almost always owns the long horizon. And fourth, post-occupancy evaluation and evidence-based design exist to bring data into the room when stakeholders disagree. When the question is about resolving competing opinions, the answer that cites POE data or comparable facility benchmarks usually wins over the one that polls the loudest stakeholder. With that posture set, we step into section 4.1. Walk into your first campus master planning meeting and you will discover something that single building programming never prepares you for. The first building you put on the ground locks in about 80% of the campus that will follow. The central plant location, the trunk utility routing, the primary roadway hierarchy, the datum elevations across the site. Every one of those decisions cascades into every building that comes after. And once building 1 is in the ground, those decisions cannot be revisited at any reasonable cost. The architect who programs campus infrastructure for today's demand, instead of the build-out 20 years out, is the architect whose client tears out a perfectly good chiller plant in year 12, eats a 7-figure overrun, and ends up named in the lawsuit that follows when the institution looks for someone to blame. The exam tests whether you can think in decades, not in single contracts. Let me walk you through the 5 considerations that separate campus programming from single building programming. 5 layers of complexity that single building programming never touches. Shared services, the central plant, dining commons, conference center, structured parking, must be sized for peak demand across all the buildings the campus will serve, not the simple sum of each building's individual peak. Inter-building circulation, whether covered walkways, tunnels, or shuttle routes, must solve weather protection, accessibility, and wayfinding before any architect draws a single line. Infrastructure planning is the highest stakes piece because utilities, data networks, and fire protection loops must carry capacity for buildings that have not been programmed yet. Phasing demands that each early building function as a complete, usable facility before later phases arrive. There is no half-functional building 1 in occupancy. And each building's identity within the campus hierarchy must balance individual character against the cohesion the institution wants the campus to project. Each of those 5 layers ties back to a sizing question that the program must answer before any building gets designed. 6 resource categories, each one with a sizing question the program must answer before the master plan can hold up to scrutiny. The central plant, chillers, boilers, cooling towers, needs a diversity factor analysis because peak loads from individual buildings do not stack 1-to-1. The campus peak is almost always lower than the sum of the parts. Distributed utilities need trunk capacity sized for full build-out and branch capacity sized by phase, because pulling open a finished quadrangle to add a chilled water main in year 10 is the kind of cost that gets architects named in deposition transcripts. Shared program spaces, dining, conference, fitness, library, need per capita seat ratios calibrated to the population the campus serves at full enrollment, not at opening day. Parking and transit need a modal split assumption and the relevant zoning ratios. Stormwater needs an impervious area calculation at full build-out against the permitted discharge. And site amenities need a clear identity standard, so each new building does not negotiate the campus brand from scratch. 5 of those decisions are locked into place the moment Building 1 goes in the ground. The program has to flag them as Phase 1 lock-ins. Here are the 5 Phase 1 decisions that lock in roughly 80% of the future campus, and every one of them must be documented as a lock-in item in the master plan, with explicit owner sign-off. Central plant location and trunk utility routing top the list, because relocating either one after Building 1 is occupied carries a cost premium that can swallow a year of project profit. The primary entry sequence and the roadway hierarchy set the front door of the campus. Every future building reads itself against that entry. Datum elevations and the grading strategy across the site cannot be revisited cheaply once Building 1 sets the finished floor reference plane. Loading and service circulation will be shared by every future building, so getting the loop wrong sentences a delivery driver to circle the campus for the next 30 years. And the signage and wayfinding architecture establishes the campus brand framework that every future building inherits. Skip any of these 5 during programming, and the owner pays in fee disputes, redesign cycles, and depositions for the rest of the campus's life. Let me close with the 5 takeaways that anchor everything in this section. 5 takeaways from campus programming. Building 1 locks in roughly 80% of the future campus, so the program for that first building is really a program for the whole institution. Sizing shared services, central plant, dining, parking, demands a diversity factor analysis, not a naive sum of building peaks. Utility trunks must carry full build-out capacity from day 1, with branch capacity scaled by phase. 5 Phase 1 lock-ins: plant location, entry hierarchy, datum elevations, service circulation, and signage architecture demand explicit owner sign-off in the master plan because none of them can be revisited cheaply. And each early phase must function as a complete, usable building before later phases arrive, because there is no half-functional building 1 in occupancy. Most architects sit through their first phase project kickoff thinking they are saving the owner money. You are not. A phased build runs roughly 15 to 25% more than a single continuous construction effort. And the architect who fails to surface that premium during programming is the architect who gets named in the fee dispute claim when the owner discovers it mid-construction. The reason owners underestimate the premium is structural. Each individual phase looks small on its own. The duplicated mobilization, the oversized Phase 1 foundations, and the year-over-year escalation never appear in any single contract, so the cumulative cost only becomes visible when somebody totals all the contracts together. Get this premium into the program phase budget, get explicit owner sign-off on it, and you will not be the one explaining it to a deposition transcript later. Let me walk you through the 5 phasing strategies and where each one actually fits. 5 phasing strategies, each tied to a project type where it works. Horizontal expansion adds new wings alongside the existing footprint, the right pick for hospitals, schools, and research campuses where land is available. Vertical expansion adds floors on top of an existing structure, the move for tight urban sites where there is nowhere else to go, but it requires Phase 1 foundations and columns oversized for the eventual load. Interior fit-out builds the shell now and finishes interiors later, the speculative office play, where the future tenant is unknown. Swing space temporarily relocates the existing occupants while the building they live in is renovated, essential for hospitals and labs that cannot shut down. And decant and backfill moves occupants out of Building A into Building B, renovates A, then shuffles new occupants in. The standard play for phased campus-wide renovation. Pick the wrong strategy and you redesign the program halfway through construction. The 2 strategies architects confuse most are horizontal and vertical, and the cost implications are not the same. Horizontal and vertical expansion look similar on a master plan, but they make very different demands on the Phase 1 program. Horizontal expansion needs available land alongside the first building. If the site does not have it, the strategy is off the table. The Phase 1 structure carries only its own load, so foundations and columns are sized normally. Disruption to occupied Phase 1 stays low during the expansion because the work happens on adjacent ground. And each phase can be bid as an independent contract, which simplifies procurement and reduces risk. Vertical expansion is the opposite story. It needs no extra land. That is why it works on urban infill. But it loads Phase 1 with an oversized cost premium. The columns and foundations must be sized for the full eventual building. MEP shafts and elevator overrun must be reserved in the Phase 1 cores. And the disruption to occupied Phase 1 during the buildup is severe. Architects who do not surface those Phase 1 oversize requirements during programming get sued when Phase 2 lands on a structure that cannot carry it. Whichever strategy the owner picks, the program must capture the cost drivers behind that 15 to 25% premium. 5 cost drivers that combine to produce the 15 to 25% phasing premium, and every one of them belongs in the program phase budget, so the owner sees them before the contracts are signed. Duplicated mobilization and demobilization for each separate phase contract. The contractor sets up the site, tears it down, and comes back a year later to set up again. And every cycle carries fixed costs that a single continuous build pays only once. Oversized Phase 1 structure built to receive Phase 2 loads. For a vertical strategy, this is the single largest line item, and for a horizontal strategy, the foundations at the wing intersection still need work. Temporary partitions, weather closures, and barrier walls that separate construction from occupied space. These are pure carrying costs that produce nothing permanent. Cost escalation between phases compounds at roughly 3 to 5% per year, which on a 5-year phased build adds up to a 15 to 25% layered increase by itself. And lost productivity from trades working in or beside occupied buildings, slower schedules, restricted hours, dust protection protocols, closes out the list. Let me close with the 5 takeaways the exam keeps testing on phase development. 5 takeaways from phase development. Phased projects cost roughly 15 to 25% more than equivalent continuous builds, and owners almost always underestimate the premium until the architect surfaces it during programming. There are 5 strategies: horizontal expansion, vertical expansion, interior fit-out, swing space, and decant and backfill, each tied to a specific site and program condition. Vertical expansion uniquely forces oversized Phase 1 structure, foundations, and MEP cores, and skipping those provisions during the program produces a project that cannot be built as planned. The premium itself comes from 5 drivers: duplicated mobilization, oversized Phase 1 structure, temporary partitions, year-over-year escalation, and lost productivity. And the architect's job is to capture all of that in the program phase budget with explicit owner sign-off before any contract is signed. You are programming a mixed-use building: residential on the upper floors, office in the middle, retail at the base. Most architects walk into that project thinking of it as one building. It is not. Mixed use is 3 different code classifications, 3 different structural grids, 3 different MEP operating schedules, 3 different parking demand profiles, and 3 different sets of users who do not want to share an elevator. Every one of those conflicts must surface during programming because design phase discovery means you redesign whole floors. The architect who lets a residential over office structural grid mismatch slip past the program is the architect who finds out about it during foundation review, eats the redesign on overhead, and gets sued by the developer for the schedule slip. The exam wants to see you naming the conflicts before they become claims. Let me walk you through the 5 conflicts that programming has to surface for any mixed-use building. 5 conflicts that mixed-use programming has to surface before any line gets drawn. Separate entries first. Each use type needs its own entrance and lobby because retail customers do not share elevators with residential tenants, and the program has to lay out the circulation to keep them separated from the ground floor up. Code separation is the legal piece. Different occupancy types under IBC require rated assemblies between them, and the rated floors and walls drive everything about floor planning. Structural variation hits the architect who has only done single-use buildings. Residential grids run tight, office grids run wider, retail grids want to be column-free, and reconciling them takes deliberate program phase coordination. Parking ratios differ by use, and crucially, they peak at different times. Office at 9 a.m. on Tuesdays, restaurant at 7 p.m. on Saturdays, which sets up the shared parking opportunity in the next frame. And MEP zoning has to give each use its own HVAC operating schedule and plumbing demand, because running an empty office floor at 70 degrees overnight to keep the residential tower above it warm is a cost no owner accepts. Most of those conflicts trace back to one larger choice: how much flexibility the building is programmed to carry. Rigid and flexible programming approach the same building from opposite ends. A rigid program is sized tight to today's use, which produces a lower first cost but locks the building into one program for its life. Floor-to-floor heights are set to the current use, structural grid is optimized for one use type, and any future renovation is structural, which means it is expensive. A flexible program carries a higher first cost because the MEP capacity, the floor-to-floor height, and the structural grid all carry headroom that today's program does not need. Floor-to-floor adds roughly 6 inches to allow a future use change. The structural grid lands on a generic dimension, like 30 by 30, that accommodates multiple uses. And the MEP infrastructure carries capacity for loads that have not arrived yet. The trade-off is straightforward. Pay more today for a building that adapts, or pay less today for a building that needs to be torn apart in 15 years. Hospitals and labs accept the rigid path because their programs are stable. Speculative office and university buildings almost always pick flexible because their programs will not be. One specific flexibility decision pays back faster than any other: shared parking across mixed uses. 20 to 30%. That is the parking reduction shared parking analysis routinely justifies for a mixed-use project, and the exam tests this concept directly. The mechanism is offsetting peak demand, where office peaks weekday business hours, restaurant peaks evenings and weekends, and residential peaks overnight. Summing each use's code minimum requires every space to be present for the worst case of all three, which never happens. The ULI shared parking methodology calculates the actual combined peak across an hour-by-hour profile and almost always shows a meaningful reduction. Many municipalities now permit this analysis in their zoning code, which means the variance process is straightforward when the architect documents the math in the program. 20 to 30% fewer spaces can free up an entire structured parking level worth of construction cost, and the owner who never sees that analysis pays for parking that physics says was never needed. Let me close with the 5 takeaways the exam consistently tests on mixed use. 5 takeaways from mixed-use programming. Combining multiple uses in one building multiplies the code, structural, and MEP complexity in ways single-use programming never encounters. The 5 conflicts that programming must surface are separate entries, code separation, structural grid variation, parking ratios, and MEP zoning. And every one of them is a redesign waiting to happen if it stays hidden. A rigid program optimized to the current use is cheaper to build today, but expensive to renovate when the use changes, which it usually does. A flexible program pays a first cost premium, roughly 6 extra inches of floor-to-floor, a generic grid like 30 by 30, MEP headroom, and saves far more over the building's life. And shared parking analysis under the ULI methodology routinely cuts total parking by 20 to 30% for mixed-use projects, which is one of the highest impact moves the program can document. You hand the owner a cost per square foot number during programming, and that number gets quoted back to you for the next 18 months as if you carved it into stone. The owner builds a budget around it. The board approves the project on it. The developer pitches it to lenders, and then schematic design lands at 50% over the number you gave, because cost per square foot is order of magnitude estimating with a plus or minus 30 to 50% accuracy band, and you presented a single point. That is how architects get named in the lawsuit when the project gets cut to fit a budget that was never realistic. The exam tests whether you know which estimating method matches which design phase, and whether you present the accuracy band along with the number every time. Single point estimates during programming are professional malpractice. Let me walk you through the 4 cost estimating methods that cover programming through schematic design. 4 cost estimating methods map to the AACE accuracy framework that the exam expects you to know cold. Cost per square foot is AACE Class 5, the order of magnitude method, with a plus or minus 30 to 50% accuracy band. That is the widest band, and it is appropriate only for very early feasibility before any design exists. Cost per unit takes building type metrics like dollars per hospital bed, or per hotel room, or per parking stall. AACE Class 4 plus or minus 20 to 30%. Useful when the program is settled, but no design exists. Parametric estimating drives cost from key parameters like building perimeter, floor count, and major system selections. Also Class 4, also plus or minus 20 to 30%, used in late programming when some design parameters are known. And assembly estimating, AACE Class 3, tightens the band to plus or minus 15 to 20% at the transition into schematic design once the structural, envelope, and MEP systems are identified. Accuracy improves as the design progresses, and the architect who uses the wrong method at the wrong phase is the one explaining the variance to a deposition transcript. Class 5 cost per square foot bands vary dramatically by building type. Here are the ranges the exam keeps testing. 6 building type cost ranges drawn from RS Means 2024 national averages, and the spread within each type is the lesson. Class A office runs roughly $250 to $500 per square foot, a 2-times spread driven by location, finish level, and structural premium. K-12 schools land between $300 and $550 per square foot, with the high end reflecting community use gymnasiums and security upgrades. Hospitals are the outlier at $500 to $1,200 per square foot, reflecting the FGI infrastructure, medical gas, and redundancy requirements that make healthcare the most expensive building type to construct. Multifamily residential runs more modestly at $200 to $450. Parking structures are the floor at $60 to $120 per square foot, and laboratories climb to $450 to $1,000. The high end of every range is not the worst case. It is the expected case for a high-cost market like Manhattan or San Francisco with a premium client. Every one of those national average numbers requires 4 adjustments before you hand it to an owner. 4 adjustments. Every one of them required before a national average number is fit to give to an owner, and skipping any one is how architects produce estimates that miss the eventual bid by 30 or 40%. Location first. Apply the RS Means City Cost Index for the specific metro area, because Manhattan is roughly 1.4 times the national average, and rural Mississippi is roughly 0.7, and the same hospital program produces wildly different estimates depending on where it lands. Quality level second. A base building bid as warm shell only is not the same dollar per square foot as a signature institutional project with premium finishes, and the band in the previous frame collapses to the right number only after you place the project in the appropriate quality band. Site conditions third. Soils, contamination, demolition, and utility extension can each individually dominate the cost on a difficult site, and none of them are captured in a per SF building cost. And current market fourth. Construction labor and material costs escalate 3 to 5% in a typical year and 10 to 15% in a hot market, so the bid year matters as much as the program. Hand over an unadjusted number, and the architect owns the variance. Let me close with the 5 takeaways the exam keeps testing on cost benchmarking. 5 takeaways from cost benchmarking. Cost per square foot is AACE Class 5 estimating, with a plus or minus 30 to 50% accuracy band, and pretending otherwise is the fastest way to create a budget that cannot survive schematic design. The 4 estimating methods, cost per SF at Class 5, cost per unit and parametric at Class 4, and assembly at Class 3, tighten as the design progresses, and using the wrong method at the wrong phase is the fastest path to a claim. Always present a range during programming, because a single point gets quoted back as a commitment. 4 adjustments: location via the RS Means City Cost Index, quality level, site conditions, and current market must be applied before any national average number is delivered to an owner. And single point estimates during programming are how architects end up named in lawsuits when the project gets cut to fit a number that was never realistic. You have been told your entire career that construction cost is the number that matters. It is not. Initial construction is roughly 5 to 10% of a building's total cost of ownership over its lifespan. Operations and maintenance consume the other 90%, and the decisions that drive those operating costs, the system efficiency, the envelope thermal performance, the equipment redundancy strategy, are made during programming before a single line of design exists. The architect who optimizes purely for first cost during programming is the architect whose building costs the owner 3 times its construction cost over 30 years. And when the owner finally runs the math and discovers it, the architect is the one named in the lawsuit for the operating cost overrun nobody disclosed. The exam tests whether you can distinguish first cost from life cycle cost, and whether you can defend a higher first cost when the math supports it. The single most important number in life cycle cost analysis is the share that initial construction actually represents. 5 to 10%. That is the share of a building's life cycle cost that initial construction actually represents. The other 90 to 95% goes to operations, maintenance, and major system replacement over the building's life. This single statistic reframes every cost conversation that happens during programming. When the MEP consultant proposes a higher efficiency chiller plant that costs 15% more upfront, that 15% first cost premium is being applied to a layer that itself is only 5 to 10% of the total. And the energy savings compound against the dominant 90% for the life of the building. The trade-off math almost always favors the higher first cost, and the architect's job is to make sure the owner sees the math, not just the construction quote. Skip this analysis, and the building gets cheap systems that cost 3 times as much to run. The other 90% breaks down across 4 operating categories the program must account for. 5 life cycle cost components and the shares they typically claim. Initial cost, which is design plus construction, is the 5 to 10% we already covered, and it is the only number that ever gets press in a construction publication. Operations is the elephant at 60 to 85%, covering energy, water, staffing, and custodial, and almost every system choice made during programming influences this category for the life of the building. Maintenance covers routine upkeep, repairs, and cleaning, takes another 10 to 15%, and material durability decisions made during programming directly drive maintenance cost. Replacement spans the roof at year 25, the HVAC at year 15, the elevators at year 30, runs another 5 to 10%, and programming decisions about system quality directly extend or shorten these replacement cycles. And residual value at the end of the analysis period is genuinely variable, ranging from positive for a quality building to negative if demolition is required. The exam tests whether you can identify which programming decisions influence which component. 4 specific programming phase decisions move the needle on lifecycle cost more than anything that follows in design. 4 programming phase decisions, and every one of them moves the needle on lifecycle cost more than anything that happens later in design. Envelope thermal performance first. The U value, the air leakage target, the glazing to wall ratio set during programming lock in the heating and cooling energy consumption for the life of the building. And design phase improvements at the margins cannot recover what programming chose to forfeit. Mechanical system quality and redundancy second. Higher efficiency equipment costs more upfront, but drives operations costs down for 30 years. And redundancy decisions like N+1 versus single failure tolerance shape maintenance schedules and replacement cycles. Material durability standards third. Terrazzo lasts a century, while VCT needs replacement every 15 years. And that choice belongs in the program, not in finishes selection. And the owner's discount rate fourth. Present value math is sensitive to the rate assumption, so the program must document what discount rate the owner wants applied, because the same alternative can win or lose depending on whether the rate is 3% or 7%. Get these 4 into the program, and the owner sees the real cost. Let me close with the 5 takeaways the exam keeps testing on lifecycle cost. 5 takeaways from lifecycle cost analysis. Initial construction is only 5 to 10% of a building's total lifecycle cost, which means the construction estimate the owner cares most about is the smallest share of what the building will ultimately cost to own. Operations dominate at 60 to 85% of lifecycle cost, and almost every system choice made during programming affects this share. Higher first cost frequently produces a lower total cost of ownership, and the architect's job is to surface that math before the owner cuts the high-efficiency systems to fit a tight construction budget. 4 programming phase decisions: envelope thermal performance, mechanical system quality, material durability, and discount rate assumption drive the bulk of operating cost for the life of the building. And documenting the owner's discount rate before any LCCA comparison is the only way to keep the analysis honest, because present value math is sensitive enough to the rate that the same alternative can win or lose depending on the assumption. Most architects encounter value engineering for the first time at 50% construction documents, when the cost estimate runs over budget and the contractor walks in with a list of substitutions. Eliminate the curtain wall, swap the terrazzo for VCT, drop the cooling redundancy. That is value engineering, and at that phase, it saves 5 to 10% of project cost while triggering redesign, resubmittal, and schedule delays. You can do far better. Value analysis during programming asks an entirely different question. Not, can we build this cheaper, but do we actually need this at all? And the savings run 10 to 20% of project cost with no redesign required because nothing has been designed yet. The architect who never runs a programming phase value analysis is the one whose owner gets sued by a board for failing to challenge scope before construction docs were issued. The exam tests whether you can distinguish the two and apply them at the right phase. Let me show you exactly how programming phase value analysis differs from construction phase value engineering. 2 phases, 2 questions, an order of magnitude difference in the impact. Programming phase value analysis asks whether the scope is actually necessary. The impact is total because you can eliminate whole building elements before they are designed. The cost to change is minimal because nothing has been drawn yet, and the typical savings run 10 to 20% of total project cost. Construction phase value engineering asks whether the existing scope can be built more cheaply. The impact is limited to substitutions within what has already been designed. The cost to change is significant because every change triggers redesign and rebid and possible schedule impact, and the typical savings reach only 5 to 10% of project cost. Same word, completely different exercise. The exam will present a scenario where the owner asks for value engineering at 60% construction documents, and the correct answer is almost always to push the conversation upstream. But if it cannot be moved, you accept the smaller savings and the design rework that comes with them. When the value analysis happens during programming, the SAVE International Job Plan structures it across 6 phases. 6 phases of the SAVE International Job Plan, and the discipline of running them in order is what separates a structured value analysis from a brainstorm that produces nothing actionable. Phase 1 is information. Gather project goals, cost data, the owner's project requirements, constraints, and stakeholder requirements, because you cannot challenge scope until you know what success actually looks like. Phase 2 is function analysis. Describe each system or element using a verb-noun pair, such as support load or control temperature, and use that pair to isolate primary functions from secondary functions and the cost of each. Phase 3 is creative. Generate alternative ways to perform the required functions and explicitly defer evaluation, because the brain that judges ideas is not the same brain that generates them. Phase 4 is evaluation. Score the alternatives against cost, performance, schedule, risk, and life cycle impact, and rank the top candidates. Phase 5 is development. Take the top-ranked alternatives and develop each into a specific costed proposal with documented advantages, disadvantages, and implementation requirements. And phase 6 is presentation. Present the recommendations to the owner and design team for decision, and document accepted, rejected, and deferred items in a decision log so nobody relitigates the call 6 months later. When you sit down to run the creative phase, 4 questions repeatedly produce the biggest savings. 4 prompts that repeatedly produce the biggest savings when the creative phase of the Save Job Plan opens up the program. First, is this scope required by code, by owner program, or by assumption only? Most of what gets challenged turns out to be assumption inherited from the last project the architect did. And inherited assumptions never get challenged unless somebody explicitly asks the question. Second, can 2 adjacent rooms share a use rather than each carrying dedicated space? The conference room that is empty 4 days a week and the training room that is empty 3 days a week probably want to be one room with a movable partition, and the program phase decision saves the floor area for the life of the building. Third, is a higher performance envelope cheaper than the MEP system sized for a worse one? This is the most counterintuitive trade and the one architects miss most often, because better envelope reduces peak heating and cooling load, which downsizes the entire mechanical system. And fourth, does this redundancy match the owner's actual tolerance for downtime? N+1 redundancy is expensive, and many owners ask for it because they were told to without doing the failure mode math. Let me close with the 5 takeaways the exam keeps testing on value analysis. 5 takeaways from value analysis in pre-design. Running value analysis during programming saves 10 to 20% of project cost, while construction phase value engineering saves only 5 to 10%, an order of magnitude difference that the exam tests directly. Programming phase analysis asks whether the scope is needed at all, while construction phase value engineering only asks whether the existing scope can be built more cheaply, and only one of those questions moves the cost needle. The SAVE International Job Plan runs 6 phases: information, function analysis, creative, evaluation, development, and presentation, in that order, and the discipline of running them in order is what separates a value analysis from a brainstorm. Function analysis verb-noun pairs isolate primary from secondary cost and prevent the team from confusing the function with the form. And higher envelope performance frequently downsizes the entire mechanical system, producing combined savings that pure first-cost thinking never finds. Most architects walk into a hospital project assuming it is a slightly bigger office building with a few medical rooms tacked on. And that assumption is exactly how you end up named in a malpractice lawsuit when a code blue cart cannot reach a coding patient in time. Healthcare is the most complex building type to program, and the stakes are not measured in dollars. The stakeholder count is the largest in commercial construction. Surgeons, nurses, infection control officers, biomedical engineers, environmental services, the state health department, and the federal accreditation body all hold approval authority over different slices of the program. The regulatory base is dominated by the FGI guidelines, which most states adopt as code. The space types are specialized, with clearances measured in inches, and the adjacency requirements are the only ones in the entire ARE where the wrong answer shows up in mortality statistics. Get this wrong, and you lose your license. The disciplinary record follows you, and your insurance is sued by every plaintiff's firm in the state. The exam tests whether you can rank stakes correctly when the rooms touch each other. 5 programming essentials separate a healthcare facility from any other building type. 5 healthcare programming essentials, and none of them is optional. The FGI guidelines set the minimum room sizes, clearances, and feature requirements by room type. Most states adopt the guidelines as code, so non-compliance means the building cannot receive an occupancy certificate. Department relationships separate healthcare from every other building type. The emergency department must sit close to imaging and surgery because trauma transport time correlates directly with mortality outcomes. Intensive care must connect to surgery because the post-operative window is the most dangerous one. Separation of flows is an infection control requirement, not a wayfinding preference. Patient, staff, visitor, clean supply, and soiled material routes must all be physically distinct. A program that lets any two share a corridor will fail the Joint Commission survey. Flexibility through acuity-adaptable rooms and universal head walls lets a patient escalate from regular care to high acuity without being moved. That is itself a clinical safety improvement. And technology infrastructure must be programmed up front. Retrofitting a hospital nurse call system into a finished ceiling can run a quarter of the original installation cost. The adjacency rules deserve their own table because they are the ones the exam tests most directly. 5 adjacency rules, every one of them programming-level decisions that cannot be undone by clever design once the building is in the ground. The emergency department must be directly adjacent to imaging, surgery, and the trauma bay because every minute of transport between them changes a survival statistic, and the ED must be separated from the main public lobby and the outpatient clinics so trauma activity does not bleed into routine care. Surgery must connect to central sterile supply, the intensive care unit, and the post-anesthesia care unit, while being physically separated from public circulation and food service for infection control. The ICU needs proximity to surgery, pharmacy, and the lab because the patients in it are the ones most likely to need an emergency intervention or a stat medication. Labor and delivery must be near the neonatal ICU and the surgical suite for emergency C-sections, but separated from the general patient population. And the pharmacy must sit central to all clinical departments with a secure receiving dock, and its public access must be controlled to the level the State Board of Pharmacy requires for controlled substances. These 5 rules are programming constraints, not design preferences. There is one regulatory point the exam tests over and over again, and architects who default to thinking about the IBC miss it every time. The FGI guidelines and the International Building Code govern the same hospital, but they govern different layers of it, and confusing the two is the exam trap architects walk into most often in healthcare programming. The FGI guidelines set the minimum room sizes, the clearances around the bed, and the feature requirements by room type: operating room, patient room, isolation room, dialysis station. The FGI is adopted by most U.S. states as code through state health department regulation, which means non-compliance is enforceable, and the building will not get an occupancy certificate. The Facility Guidelines Institute updates the document on a 4-year cycle. The International Building Code, by contrast, handles the occupancy classification, the exit count and width, the structural requirements, and the fire rating minimums for the building shell. The IBC is updated on a 3-year cycle by the International Code Council. The IBC is silent on minimum patient room, or operating room, sizing. If the exam asks who sets the minimum size of a hospital labor and delivery room, the answer is the FGI, not the IBC, and architects who default to the code answer lose the question. Let me close with the 5 takeaways the exam keeps testing on healthcare programming. 5 takeaways from healthcare facility programming. The FGI guidelines, not the International Building Code, set the minimum hospital room sizes and clearances. Most states adopt the guidelines as code, and the IBC is silent on clinical room sizing. 5 flow types: patient, staff, visitor, clean supply, soiled material must be physically separated for infection control, and a program that lets any two share a corridor will fail accreditation review. The emergency, surgery, and ICU adjacencies are not preferences, but clinical outcome constraints. Transport time between them correlates with mortality. Technology infrastructure for nurse call, real-time location, and physiologic monitoring must be programmed during pre-design because retrofitting it through a finished hospital ceiling can run a quarter of the original installation cost. And acuity-adaptable rooms with universal head walls let a patient escalate from regular care to high acuity without being physically moved, which is itself a measurable safety improvement. Every architect who walks into an educational programming meeting underestimates the same thing. The program is not what the principal wants this year. It is what the district policy and the state education department mandate. And those two documents do not always agree. You must balance standardization against flexibility, security against community access, and pedagogy against budget. Add the fact that the users are children, and the wrong programming decision lands you in litigation when an active shooter incident reveals an unsecured vestibule, or when a parent sues the district over inadequate special education space. Most architects treat K-12 as a generic institutional building. That is the mistake the exam catches. Schools are the building type where security has rewritten the entire program, where higher education facilities run on room utilization rates rather than enrollment numbers, and where the wrong assumption locks the district into bonded debt for 30 years. The exam tests whether you can read the building type before defaulting to commercial habits. K-12 programming starts with a fixed set of essentials that the state education department will require. 6 K-12 space standards the state education department will audit before the bond money lands. Classroom size ranges from 850 to 1,000 square feet at the elementary level. Secondary classrooms run slightly smaller at 750 to 900. The numbers vary by state, and verifying the local standard before the program is signed is the architect's responsibility, not the district's. Students per classroom drives the total classroom count. The square footage per student metric is the one the state board scrutinizes most because it includes circulation, common areas, and support spaces, not just the classroom itself. Gymnasium sizing depends heavily on whether the district intends community use after hours, which can double the required size. Media centers have been climbing in scope as districts combine library, makerspace, and instructional technology. And cafeterias size by lunch period. Running 3 rotations at 1/3 of students each cuts the required area by 2/3. Miss any of these by 10%, and the district either overbuilds or finds itself short classroomed within 5 years. Higher education flips the script. Enrollment headcount no longer drives space. 5 higher education programming considerations, and every one of them inverts a habit carried over from K to 12. Room utilization rates are the headline. A college targets 60 to 70% utilization across the scheduling week, and that target, not the raw enrollment number, drives how many classrooms the campus actually needs. A poorly scheduled campus with 5,000 students may need more classrooms than a well-scheduled campus with 7,000. Research space varies more wildly than any other higher ed type. Wet labs, dry labs, computational suites, makerspaces, and performance halls all live under the same departmental umbrella, with vastly different cost per square foot numbers. The trend toward shared classrooms across departments reduces dedicated space and lifts utilization. Residential life programming must address living, studying, socializing, and dining in an integrated way, not as separate building programs. And every individual building program must align with the campus master plan, because a building that fits its own program but breaks the campus pedestrian network or central plant capacity is a programming failure that no design phase can rescue. There is one programming dimension that has rewritten K-12 in the last 20 years, and now bleeds into higher ed too. 5 security-driven programming requirements that have rewritten the K-12 program in the last 20 years and now bleed into higher education as well. Controlled single-point entry with a secure vestibule between exterior and interior doors is the new minimum baseline. Anyone entering the building during school hours has to pass through a vestibule visible to the administrative reception position. Lockdown capability is the next layer. every classroom door must lock from the inside without a key, because the teacher must be able to secure the room in seconds without crossing the hall. Visual supervision of all entries from administrative or reception positions means the program must place the front office in line of sight to the entry, not buried in a back wing. Compartmentalization of building wings limits how far an intruder can move through the school once inside, and it must be planned during programming, not retrofitted as a corridor after the fact. And threat-resistant glazing at the main entry and at all ground floor public-facing windows has become standard practice. Districts that skip it lose access to state security grant funding. Miss any of these in the program, and the district faces a lawsuit the next time a parent watches the news and asks why their school does not look like the one in the headline. Let me close with the 5 takeaways the exam keeps testing on educational facility programming. 5 takeaways from educational facility programming. K-12 space standards are state mandated, and verifying the local rules before the program is signed is the architect's responsibility, not the district's. Higher education programming runs on room utilization rates rather than enrollment headcount, and a well-scheduled campus needs fewer classrooms than a poorly scheduled one, even at higher enrollment. The trend towards shared classrooms across departments is the higher education efficiency lever, because dedicated departmental space caps utilization, and the cap is what drives overbuilding. Security in K-12 is programming, not a design afterthought. Controlled single-point entry, lockdown capability, visual supervision, compartmentalization, and threat-resistant glazing all belong in the program document. And campus master plan alignment beats individual building optimization every time. Because a building that fits its own program but breaks the campus utility loop or pedestrian network is a programming failure no design phase can rescue. You can sketch a generic office floor plate in your sleep, and that is exactly the problem. Most architects program office and residential buildings on muscle memory from projects they did 5 and 10 years ago, and the muscle memory is now wrong. Post-pandemic work patterns cut required office area by 20 to 40% at many tenants. The growth of remote work changed what residential tenants demand from a unit, and both effects landed during the same 5-year window. Get this wrong, and your developer client builds the wrong number of square feet, runs the pro forma into the ground, and personally sues you for the leasing shortfall when the building underperforms. The ARE is now actively testing both shifts because NCARB is watching the market. The exam tests whether you can carry current programming numbers, not the ones in last decade's textbook, and whether you understand which building efficiency lever the developer cares about most. Office programming now spans 4 distinct approaches, and the square footage gap between them is huge. 4 office approaches, and the square footage spread between them is roughly 5 to 1, which means the workplace decision in the program is worth more than every other line item in the office program combined. Traditional enclosed offices need 200 to 300 square feet per person and offer privacy and acoustic control, but they kill flexibility and block daylight from reaching the floor plate. Open plan drops to 80 to 150 SF and gains flexibility and daylight, but introduces noise and distraction that destroy focused work productivity if the acoustics are not deliberately designed. Activity-based working pushes efficiency to 60 to 100 SF with unassigned seating, but it only succeeds if the client's organizational culture supports it. Drop ABW on a culture that wants assigned desks, and the tenant will retrofit assigned seating within 18 months. Hybrid models balance enclosed and open at 100 to 175 SF. The exam may present a scenario and ask which approach fits a specific organizational culture, and the right answer is rarely the most efficient one. It is the one the culture will actually use. Residential programming runs on 5 metrics that the developer's pro forma is built on. 5 residential programming metrics, and every developer pro forma is built on them in this order. Unit mix. The percentage of studios, 1-bedroom, 2-bedroom, and 3-bedroom units is the first decision and the one most driven by local market data, not architect preference. The mix typically leans heavy on 1- and 2-bedroom units in urban markets because that is what the rental absorption rate supports. Net to gross efficiency is where the architect's contribution shows up most. Double-loaded corridor slabs run 80 to 87% net to gross because a single straight corridor serves units on both sides and maximizes leasable area against the gross. Point towers drop to 70 to 80% net to gross because each floor carries a full elevator and stair core for fewer units. Parking ratios run half a space to 2 spaces per unit, depending on transit access. Manhattan is half, suburban Texas is 2. Amenity space lands at 15 to 30 square feet per unit. And unit sizes follow predictable ranges, from 400 square feet for studios up to 1,200 for 2 bedrooms. Miss any of these by 10%, and the pro forma underwriting goes negative, and the architect is sued when leasing stalls. There is one number the exam tests directly on mixed-use sites, and it makes a real dent in the parking program. 20 to 30%. That is the typical reduction in total parking spaces possible on a mixed-use site when office and residential share the same structure. The math behind the savings is simple, and the exam tests directly on it. Office parking peaks weekday business hours between 9 a.m. and 6 p.m. Monday through Friday. Residential parking peaks evenings and weekends when the office tenants are gone. The two demand curves rarely overlap, so a shared parking analysis can show that a mixed-use building needs roughly 70 to 80% of the parking count that each use would need on its own. The savings are real cash for the developer. At $30,000 to $50,000 per structured parking stall, eliminating 100 spaces saves $3 to $5 million on the project. The architect who runs the shared parking analysis and presents it to the developer during programming is the architect who keeps the project alive when the pro forma is tight. Skip it, and the developer either overbuilds parking or kills the project entirely, and the architect's fee evaporates either way. Let me close with the 5 takeaways the exam keeps testing on office and residential programming. 5 takeaways from office and residential programming. Office square footage per person spans 60 to 300 across the 4 approaches, which means the workplace strategy decision in the program is worth more than every other office program line item combined. Activity-based working only succeeds where the client's organizational culture supports unassigned seating. Dropping it on a culture that wants assigned desks produces an 18-month retrofit. Double-loaded corridor residential hits 80 to 87% net to gross because a single corridor serves units on both sides. Point tower residential drops to 70 to 80% because each floor carries a full elevator and stair core for fewer units. And shared parking on mixed-use sites cuts total parking spaces by 20 to 30% because office and residential demand curves rarely overlap. The math is simple, the savings are real, and the architect who runs the analysis is the one who keeps the project's pro forma alive. Every architect with a programming project has the same instinct in the first stakeholder meeting. Give everyone equal time. Listen to everyone equally. Treat every voice as carrying equal weight. That instinct is wrong, and it is the instinct that gets architects fired at 60% construction documents when a senior executive who was ignored during programming finally engages and orders a redesign. You cannot give every stakeholder equal attention, and the program that tries to do that produces a watered-down compromise that nobody owns. The power interest grid is the triage tool that separates the few stakeholders whose buy-in determines project survival from the many whose input is merely useful. Skip the triage, and you face the lawsuit that follows when the architect is named for failing to surface a major program risk that the engaged stakeholders all warned about, but the disengaged power holder never heard. The exam tests whether you can categorize stakeholders correctly and match the right engagement intensity. The grid divides stakeholders into 4 quadrants, and each one carries a different engagement strategy. 4 quadrants on the power interest grid, and the engagement strategy for each one is sharply different. Key players sit in the high power, high interest corner, typically the owner, the operating sponsor, and senior leadership. And they need close, active management and direct involvement in every meaningful decision. Keep satisfied stakeholders carry high power but low interest, and they are the most dangerous quadrant on the entire grid. They have authority to override decisions, but they do not engage day to day, so the architect must proactively keep them informed and address concerns fast, without burying them in detail that drives them further from the project. Keep informed stakeholders have high interest but low formal power, and the strategy is to channel their enthusiasm and address their concerns. They often become useful project champions. Monitor stakeholders sit in the low power, low interest corner and need only periodic updates, with the architect watching for any sign that a position has changed and a quadrant move is happening. The exam tests whether you can place a stakeholder in the right quadrant and apply the matched strategy. Power and interest are easily confused in practice, so it is worth pulling them apart explicitly. 2 different axes on the grid, and confusing them is the most common scoring error architects make in stakeholder analysis. Power refers to the stakeholder's ability to affect the project, budget authority over funding, approval authority for formal sign-off, political influence as the informal version of approval, and outright veto power held by a single actor able to stop the project unilaterally. Interest refers to how much the project affects them or how much they care about it, measured in daily impact, personal investment, willingness to spend time on engagement, and emotional stake in the outcome. A senior executive may carry high power but very low interest. They have veto authority but do not attend any meetings. A frontline user may carry high interest but very low formal power. They live in the building every day but have no sign-off rights. The exam often presents a scenario where these 2 are mismatched and asks which engagement strategy applies, and the right answer hinges on placing the stakeholder on both axes independently. Stakeholders also move between quadrants as the project evolves, so the grid is not a one-time exercise. It must be refreshed at each milestone. Of all 4 quadrants, the high-power, low-interest one deserves a closer look because it is the one that blows up programs. 5 red flag patterns that signal a high-power, low-interest stakeholder, and missing any of them is the single most common stakeholder management error on programming projects. The senior executive who skipped every programming workshop but signs off on the design is the textbook case. They engage at the last minute with full authority to demand changes, and they almost always do. The board member who reads only the executive summary and votes the funding is the same pattern in a different costume. When the design is presented, they will catch one item that does not match their mental model and force a revision. The lender's representative who attends one meeting and then disappears holds approval authority over draws and can refuse a disbursement that stalls construction for weeks. The legacy donor whose name is on the building but delegates everything to staff still carries social authority that can override the program. And a single donor complaint to the board overrides every recommendation the architect produced. And the regulator who never attends but whose written approval is the final gate can require redesign at the 11th hour. The architect must seek input from each of these proactively, even when they seem disengaged. Skip the proactive outreach, and the redesign costs the architect a full re-fee. Let me close with the 5 takeaways the exam keeps testing on stakeholder prioritization. 5 takeaways from the power interest grid. Power and interest are independent axes. A stakeholder can be high on one and 0 on the other, and the grid only works when they are scored separately. The high-power, low-interest quadrant is the most dangerous on the grid because those stakeholders ignore programming and then engage late with full authority to force major changes. Key players in the high corner need active management and direct involvement in every decision, while monitor stakeholders in the low corner need only periodic updates. Stakeholders move between quadrants as the project evolves, so the grid is not a one-time exercise. It must be refreshed at each major milestone. And proactive outreach to disengaged power holders, even when they seem unengaged, prevents the late-stage redesign that costs the architect a full refee and can land them in a contract dispute over scope expansion. Most architects approach a 100-stakeholder project the same way they approach the last 20-stakeholder project. Schedule individual interviews and run more workshops, and trust that more engagement equals better programming. That instinct is the one that produces a programming phase that runs 3 months over schedule, costs the architect personally in unbilled hours, and still misses the program risk the owner sues over 6 months later. You cannot interview 200 staff individually. You cannot run a workshop that captures the input of a neighborhood association of 300 residents. And running every group through the same engagement intensity wastes energy on stakeholders who do not need it and starves the ones who do. Large group engagement is a structural design problem, not a scheduling problem. And the architect who treats it as scheduling is the one whose program drifts off target until the budget is committed and the redesign is too expensive to fix. The exam tests whether you can match the technique to the group size. 5 engagement strategies scale to large groups, and each one has different strengths and limitations. 5 large group engagement strategies, each one with a different trade-off between reach and depth. Representative committees select a few individuals to speak for larger constituencies. The strategy is efficient because it captures deep input from a manageable number of people, but it risks not reflecting the full diversity of the represented group. Tiered engagement creates a steering committee with decision authority, advised by working groups that inform but do not decide. The hierarchy is clear, but the lower tiers can feel marginalized if their input is consistently overridden. Online surveys reach everyone and produce quantifiable results, but they sacrifice depth and frequently return response rates below 20%. Open houses with staffed stations let visitors self-select topics at their own pace and handle large attendance well. The limitation is that vocal minorities can dominate the conversation while quieter stakeholders contribute nothing. And digital platforms reach remote stakeholders conveniently, but they exclude anyone without reliable technology access and require active moderation to stay productive. The exam tests that no single technique works at every scale, and a well-designed engagement program almost always combines 2 or 3. The right combination depends entirely on how many stakeholders the project actually has. 4 group size brackets, and the right engagement technique flips sharply at each break. At tens of stakeholders, meaning 10 to 50 people, workshops, focus groups, charrettes, and structured interviews with every member are all feasible, and you can drive to consensus in the room. Surveys at this scale work poorly because responses are identifiable and candor drops. At hundreds, meaning 50 to 500, interviewing everyone is impossible, so the structure becomes a steering committee at the top, 2 or 3 topic-specific working groups below, 1 or 2 town halls for the broad population, and a targeted survey instrument. At thousands, meaning 500 to 5,000, representative committees become the primary input channel, supplemented by online surveys for breadth and open houses or digital platforms for reach. Workshops as a primary method are logistically infeasible at this scale and burn out the design team. And at tens of thousands or more, typical for regional and public infrastructure projects, the work shifts to random sample surveys, deliberative polls, and formal environmental impact statement public comment processes. Pretending each individual voice carries equal weight at that scale is methodologically wrong and creates legal exposure under NEPA or state equivalents. There is one hard ceiling on engagement intensity that every architect underestimates. 5 hard limits on charrette intensity that the AHPP names directly, and every architect who has ever run a 5-day charrette knows the limits intuitively, but ignores them under client pressure. 2 to 4 days is the maximum for an intensive design charrette, before the design team and the stakeholders both burn out. Beyond 3 consecutive days, attendance drops, energy collapses, and the input quality degrades faster than the synthesis benefit grows. 6 weekly half-days outperform 3 full marathon days every time. The spacing lets stakeholders process between sessions and lets the team test ideas in the field. Each charrette day must carry a clear deliverable and an explicit off-ramp for stakeholders who cannot commit the full duration, or attendance will collapse silently in the second half. And more engagement past the diminishing returns point delays the project without yielding new information. The architect must balance thoroughness against efficiency, and the owner must approve the engagement scope and budget. Overrunning either without sign-off is the documented basis for the contract dispute that follows when the program slips into design phase. Let me close with the 5 takeaways the exam keeps testing on managing large stakeholder groups. 5 takeaways from managing large stakeholder groups. No single engagement technique works across every group size. The right approach is a deliberate combination matched to the population. At hundreds of stakeholders, a tiered structure with a steering committee, working groups, and broad town halls beats the impossible alternative of interviewing everyone individually. At thousands, representative committees plus targeted surveys plus open houses with staff stations are the practical scaling toolkit. Charrettes cap at 2 to 4 days before fatigue degrades input quality faster than synthesis benefits accumulate, and 6 weekly half-days consistently outperform 3 consecutive marathon days. And more engagement past the diminishing returns point is a project killer, not a virtue. It delays the program, burns out the design team, and frequently does not surface new information. The architect's job is to balance thoroughness against efficiency, and to document the engagement scope so a contract dispute over expanded effort never lands in the architect's lap unannounced. Most architects close out a project at substantial completion and walk away from any opportunity to find out whether the building they programmed actually performs the way the program promised. That walkaway is the single biggest source of programming malpractice in the profession. You delivered a building that meets every line item in the program document, and a year into occupancy, the energy consumption runs 20% over the modeled prediction. The conference rooms sit empty 4 days a week, and the staff has installed white noise machines because the open plan is unworkable. You are about to program the client's next building with the same assumptions. The owner sues when the second building has the same problems, and the architect cannot defend the program because nobody ever measured the first one. Post-occupancy evaluation is the only feedback loop that closes the gap between what was programmed, what was designed, what was built, and what actually works in real use. Skip it, and you program the next project on hope, which is professional malpractice waiting for a plaintiff's attorney to discover it. 5 POE methods cover the spectrum from soft satisfaction surveys to hard energy data. 5 POE methods, and they range from soft satisfaction data to hard energy meter readings, with each method producing a different category of feedback to the next program. Occupant surveys capture satisfaction, comfort, productivity, and complaints, and they reveal which space types consistently underperform in the user's lived experience. Space utilization studies track how often spaces are actually used and by whom, and they routinely expose conference rooms sized for 50 when only 6 people show up, or training rooms reserved daily and used quarterly. Environmental monitoring of temperature, lighting, acoustics, and indoor air quality validates whether the design assumptions actually held up in real operation, or whether the modeled performance was optimistic. Energy analysis compares actual consumption to the predicted load. the gap is almost always a programming assumption that did not survive contact with reality. And the calibration feeds directly into the next program's energy targets. And behavioral observation reveals how people actually use the space versus how the program intended them to use it, exposing the unanticipated workarounds that signal a real programming miss. POE closes the feedback loop. Without it, the next program is a guess. There is a more rigorous version of POE that the exam tests by name, and it deserves its own contrast. Two related practices with sharply different rigor levels. Post-occupancy evaluation measures one specific building's actual performance and informs the next program of the same client or type. It is project-specific feedback. The methodology varies project to project. The findings are rarely published outside the design team, and the value is concentrated in the architect-client relationship that runs across multiple projects. Evidence-based design, by contrast, draws on peer-reviewed research that aggregates findings across many projects and many buildings. It is used during programming to choose between design alternatives based on documented outcomes rather than designer preference. EBD methodology is standardized through industry guides like those from the Center for Health Design, and the findings are published in peer-reviewed journals that the client's risk management team can cite when defending the program. EBD was pioneered in healthcare, where patient outcomes can be measured with clinical-grade rigor, and it is now spreading to education, workplace, and other building types as outcome metrics develop. The exam treats EBD as a higher standard than POE, and tests whether you know when to apply each. There is one specific exam question on POE that gets asked over and over. 5 timeline points on POE that the exam tests directly, and architects miss them most often by placing POE in the wrong phase. First, POE happens after occupancy of one project. It is not a design phase or construction phase activity, and treating it as one is the most common exam trap error. Second, POE informs the programming of the next project, which means the feedback loop only closes when the architect or owner actually carries the findings forward into a new program. Third, POE is not free, and it is not part of the standard AIA scope. The owner must contract for it as additional services, and the program must surface that fact during initial scope negotiation so the architect is not eating the cost. Fourth, a soft POE at 6 months captures early occupancy issues like commissioning problems and acoustic complaints, while a full POE at 12 to 24 months captures the seasonal energy data and the settled occupancy patterns the early survey misses. And fifth, the owner must contract and pay for POE. The architect who provides it pro bono creates a precedent that becomes a fee recovery problem on every future project. Get any of these wrong on the exam, and you get the question wrong. Let me close with the 5 takeaways the exam keeps testing on POE and evidence-based design. 5 takeaways from post-occupancy evaluation and evidence-based design. POE happens after occupancy of one project and informs the programming of the next. It is not a design phase or construction phase activity, and confusing the timing is the most common exam error. 5 POE methods span the spectrum, from soft occupant surveys through space utilization studies to hard energy meter readings, and each one feeds back to a different category of programming assumption. Evidence-based design adds the peer-reviewed research rigor that POE alone lacks, pioneered in healthcare, where outcomes can be clinically measured, and now spreading to education and workplace. Soft POE at 6 months captures early commissioning and acoustic issues, while full POE at 12 to 24 months captures seasonal energy data and settled occupancy patterns. And POE is additional services. The owner must contract for it and pay separately, and the architect who provides it pro bono creates a fee recovery problem on every future project. Most architects underestimate how consequential site selection actually is. Every other pre-designed decision can be revisited, The program can be edited, the budget can be re-baselined, the schedule can be re-sequenced. The site cannot be unwound after acquisition. A poor site choice cannot be fixed by good design. And the architect whose client closed on the wrong site is the architect who gets sued by the owner trying to recover the design fees burned, forcing a 5-acre program into a 3-acre parcel. The April 2026 NCARB exam pivot makes this worse for unprepared candidates. PA Objective 4.5 has been narrowed to site selection, budget, schedule, and compliance. Review, not propose and develop. The exam now wants you to evaluate what was given, flag risks and gaps, and report findings, not to invent options from scratch. Get the mindset wrong on exam day, and you fail a question you would have passed under the old framing. The right answer is usually analyze and report, not propose and develop. Site selection runs on 7 criteria categories that the architect helps the owner score. 7 categories of site selection criteria, and the relative weight among them shifts dramatically by building type. Location often carries the highest weight because proximity to users, transit access, and visibility drive whether the building succeeds commercially or institutionally. Size and configuration are critical because the site must actually fit the program, including expansion potential the owner may want in 10 years. Access is high weight for every building type and covers road access for vehicles, pedestrian connections, and dedicated service access for deliveries and trash. Utilities matter because the extension cost from a remote site can run hundreds of thousands of dollars and can flip the financial feasibility entirely. Environmental constraints like flood zone designation, wetlands, soil contamination, and endangered species habitat can be absolute deal breakers. NEPA or state equivalent review may add years to the schedule. Regulatory constraints like zoning, height limits, and historic district overlay can also kill a project outright. And cost must fit the owner's budget across both acquisition and the site development premium the parcel carries. The exam tests which criterion matters most for which project type. The mechanics of weighted scoring are simple, but the order matters, and the exam tests the order. A worked weighted scoring example, and the lesson is in the sequence, not in the arithmetic. 5 criteria, each one weighted by the owner's priority before any site is scored. Location at 30% reflects this project's highest priority. Size at 25% and access at 20% fill the middle. Utilities at 15% and cost at 10% round out the rubric. Site A scores high on location and utilities and weak on cost. Site B scores high on size and cost and weak on utilities. The weighted totals land at 7.2 versus 7.0, close enough that any rounding error could flip the result. The critical exam point is the sequence. The weights must be established before the sites are scored, because once a preferred site is known, there is an irresistible temptation to adjust weights to justify it. That kind of after-the-fact adjustment is the basis for the deposition question that catches the architect. Why did the location weight jump from 20 to 30% between the first and second scoring round? Get the order wrong, and the entire defensibility of the analysis collapses. The April 2026 NCARB pivot changes how the exam tests this objective, and it deserves its own frame. 5 hard points on the April 2026 NCARB exam pivot for PA Objective 4.5, and every architecture candidate sitting after that date must internalize all 5 or fail questions they would pass under the old framing. First, the objective has been narrowed to site, budget, schedule, and compliance review, not propose and develop. Second, the exam questions ask you to evaluate what the owner has presented, a site that has been identified, a budget that has been set, a schedule that has been drafted, and to flag what is wrong with it. Third, the correct answer is usually analyze and report, not develop and create. Every multiple choice option that starts with the verb propose is likely the wrong answer. Fourth, the right response flags risks, gaps, and nonconformities in what was given to you. A zoning variance the owner did not notice, a utility extension cost the budget did not include, a schedule that did not account for environmental review. And fifth, you must practice the review mindset before exam day, because every instinct from architecture school defaults to propose and develop. Get this wrong, and you fail at least 3 to 5 questions you would otherwise have answered correctly. Let me close with the 5 takeaways the exam keeps testing on site selection. 5 takeaways from site selection and the April 2026 NCARB pivot. A poor site choice cannot be fixed by good design. Every other pre-designed decision can be revisited, but the site cannot be unwound after acquisition. 7 criteria categories: location, size, access, utilities, environmental, regulatory, and cost frame the evaluation, and the relative weights among them vary dramatically by building type. Weights must be established before sites are scored, never adjusted after a preferred site is known, because after-the-fact adjustment destroys the defensibility of the analysis in any future dispute. The April 2026 PA 4.5 exam pivot demands a review mindset, not the propose and develop habits architecture school instills. And the correct exam answer is now usually analyze and report, flag risks, gaps, and nonconformities in what the owner has presented, rather than inventing options from scratch. You are not a financial analyst, and the exam will not ask you to underwrite a real estate transaction. But every architect who walks into a developer-client meeting without understanding the basic mechanics of a pro forma is the architect whose contribution gets dismissed when the developer's underwriter pushes back on the program. The building you program either generates a financial return that supports the debt service, or it does not get built. You cannot advocate for a 5-story building over a 4-story building, or for a higher net-to-gross ratio over a lower one if you cannot explain the dollar impact in the developer's language. The architect who can speak the financial layer fluently is the one whose programming recommendations get adopted. The architect who cannot is the one who gets sued when the project goes negative, and the developer looks for someone to blame for the overbuilt common areas. The exam tests whether you understand the concepts well enough to defend programming decisions in financial terms. 6 pro forma components frame the developer's financial decision. 6 pro forma components, and every one of them connects to a programming decision the architect either champions or fails to advocate for. Gross revenue represents total potential rental income at full occupancy and drives how much building the owner can actually afford to construct. Vacancy allowance typically runs 5 to 10% and reduces effective revenue, which feeds back into building size decisions. Operating expenses cover taxes, insurance, maintenance, and management, and higher building efficiency directly reduces operating cost per leasable square foot. Net operating income, what remains after vacancy and operating expense are removed from gross revenue, is the number that has to support the debt service the lender requires. The capitalization rate is gross income divided by property value and is market-driven by the local return expectation. And return on investment is the owner's final go or no-go metric. The architect's most direct contribution to this whole stack is the building efficiency ratio, the percentage of gross building area that is actually leasable. More leasable area from the same gross footprint means more income at no additional construction cost. And the developer notices that ratio more than any other programming output the architect produces. The efficiency ratio impact deserves a specific number because it is where the architect's recommendations meet the developer's wallet. 15 to 20%. That is how much more leasable area the same gross building delivers at 85% efficiency compared to 70% efficiency. The number matters because it is where the architect's contribution to financial feasibility shows up most directly. On a 200,000 square foot gross building, a 15% gain in efficiency yields roughly 30,000 additional leasable square feet at no additional construction cost. At an average rent of $40 per leasable square foot annually, that is $1.2 million per year in incremental revenue, year after year for the life of the building. Compound that over a 30-year analysis period at a 6% discount rate, and the present value of the efficiency gain is well over $15 million. The developer who watches the architect push the efficiency ratio from 70 to 85% during programming watches $15 million of present value revenue appear in the pro forma. The architect who never advocates for efficiency, or who silently accepts a low ratio because nobody asked, is the one whose programming work never gets credited, and whose fee proposals never improve. There is a specific exam trap on financial calculations that catches careful candidates who try to over-engineer the math. 5 things you must not do on the ARE financial feasibility questions. First, do not try to perform complex financial calculations. The exam tests conceptual understanding, and any question that appears to require multi-step NPV math is probably a question where you are meant to identify which concept applies, not crunch the number. Second, do not memorize specific cap rate or return on investment numbers, because those vary by market and by year, and the exam will not test memorization of market data. Third, do not treat first cost reduction as automatically beneficial. Life cycle cost almost always favors a higher first cost when the operating cost savings compound, and the exam rewards the candidate who recognizes the trade-off. Fourth, do not assume the developer's financial metrics. Those numbers shape programming decisions and must be carried in the program as documented assumptions, not invented by the architect. And fifth, do not advocate for design quality on the exam without quantifying its revenue impact. The wrong answer is a vague claim that the building will be more attractive. The right answer is a specific connection to leasing rate, absorption velocity, or occupancy stability. Architects who try to defend design intent on aesthetic grounds alone fail every financial feasibility question. Let me close with the 5 takeaways the exam keeps testing on financial feasibility. 5 takeaways from financial feasibility. 6 pro forma components: gross revenue, vacancy allowance, operating expenses, net operating income, capitalization rate, and return on investment frame the developer's go or no-go decision, and every one of them connects back to a programming lever. Building efficiency ratio is where the architect's contribution shows up most directly, because more leasable area from the same gross footprint generates incremental revenue at no additional construction cost. The gap between 85% and 70% efficiency is 15 to 20% more leasable area, which on a 200,000 square foot building represents tens of millions of dollars of present value revenue over a 30-year period. The exam tests concepts, not complex NPV or cap rate calculations. Any question that seems to demand multi-step math is probably testing concept identification. And quantify revenue impact when defending design intent on the exam. Never advocate for design quality on aesthetic grounds alone, because that is the wrong answer every time. Most architects treat regulatory approval as a code compliance problem. That framing is wrong, and it is the framing that gets architects sued when the wetland delineation comes back at 50% CDs and tells the team that 30% of the site cannot be built on. Regulatory feasibility is not building codes. Those come later. Regulatory feasibility is the question of whether the proposed project can actually receive all the approvals it needs from every authority that touches it. Zoning, environmental review, historic district review, community approval, special permits, each one is a separate veto point, and any one of them can kill the project at any time. An architect who runs programming without explicitly inventorying every approval risk and reporting them in writing is the architect whose insurance carrier asks why the wetland study was not commissioned during programming, after the project blows up in environmental review. The exam tests whether you can recognize regulatory risk and frame it as a programming phase activity, not a design phase surprise. 5 regulatory risk areas every program must inventory before any design work begins. 5 regulatory risk areas, and each one is a potential veto point that can stop the project at any stage. Zoning is the first filter. If the proposed use is not permitted, or if the bulk envelope does not comply, the project either needs a variance or needs a different site. A variance is a high-risk path because it carries unpredictable approval timing and frequently includes conditions the owner did not anticipate. Environmental review under NEPA or state equivalents can delay projects by years, and the trigger thresholds, federal funding, wetlands, endangered species, must be checked during programming, not discovered after design has started. Historic review adds time and constraints when the site or building is listed or eligible. Community approval through conditional use permits or design review boards introduces political factors that are inherently unpredictable. And special permits, Coastal Commission, FAA height restriction, floodplain development, can be absolute deal breakers if they are not flagged during programming and worked into the schedule. Missing any of these is the documented basis for the malpractice claim that follows when the project stalls in approval. The exam tests whether you can identify which review applies to which scenario. Once the feasibility risks are inventoried, comparing alternative options needs a structured framework. A decision matrix comparing 3 alternatives across 6 weighted criteria. New construction scores highest on program fit because the building is purpose-designed, and highest on regulatory risk because new construction has fewer existing condition surprises. Renovation scores highest on schedule because the shell already exists and reasonably well on cost. Adaptive reuse scores highest on sustainability because the existing structure is preserved, but it carries the most regulatory risk because of code compliance triggers when the use changes. The weighted totals land at 6.6 for new build, 6.15 for renovation, and 5.6 for adaptive reuse. New construction wins under this rubric and these weights. The critical exam lesson is that the matrix organizes information but does not make decisions. The owner may still select a lower scoring option for reasons the matrix does not capture: a strategic relationship with a particular building, a tax credit opportunity the matrix does not weight, or a board-level commitment to historic preservation. The matrix produces a defensible recommendation, not a binding outcome, and the architect who confuses the two is the architect whose recommendation gets overridden and who then sulks instead of supporting the owner's call. Running a decision matrix correctly takes discipline that most teams skip. 5 discipline rules that separate a defensible decision matrix from a rationalization exercise. First, establish weights before any option is scored. Once a preferred option is known, the temptation to adjust weights to justify it becomes overwhelming, and after-the-fact weight changes destroy the defensibility of the entire analysis. Second, have multiple team members score options independently and then average, rather than scoring by consensus in the room. Consensus scoring produces convergence around the loudest voice, while independent scoring captures real disagreement. Third, document the source of every score, a citation, a feasibility study, or a stated assumption, so the score can be defended later when the owner asks why option B was rated a 7 on regulatory risk. Fourth, run a sensitivity analysis. Does the winning option still win if the weights shift by 10%, or if a single score changes by 1 point? If the result flips with minor changes, the matrix has not actually separated the options. And fifth, present the matrix to the owner as input to their decision, not as the decision itself. The architect advises, the owner decides, and the architect who treats the matrix output as binding is the one whose recommendation gets overridden in the next meeting. Let me close with the 5 takeaways the exam keeps testing on regulatory feasibility and decision matrices. 5 takeaways from regulatory feasibility and decision matrices. 5 regulatory risk areas: zoning, environmental review, historic review, community approval, and special permits, each function as a separate veto point that can kill a project, and every one of them must be inventoried during programming. Environmental review under NEPA or state equivalents can delay projects by years, so the trigger thresholds must be checked during programming, not discovered after design has started. Decision matrices organize information but do not make decisions. The owner may choose a lower scoring option for reasons the matrix does not capture, and that is perfectly valid. Weights must be set before any option is scored, never adjusted after a preferred option is known, because after-the-fact weight changes destroy the analysis's defensibility. And sensitivity analysis tests whether the winning option survives a 10% weight shift or a 1-point score change. If the result flips with minor changes, the matrix has not actually separated the options. Every pre-design phase ends the same way, with a recommendation to the owner that must synthesize physical feasibility, financial feasibility, regulatory feasibility, programmatic fit, and stakeholder input into a clear, defensible position that the owner can actually act on. Most architects produce a recommendation that hedges, qualifies, and refuses to commit. And that recommendation is the one the owner rejects, because it does not actually advise anything. You must commit to a professional opinion. You must state the recommended option clearly. And you must accept that the owner will sometimes choose a different one, and that the right professional response is to document the decision, document any concerns, and execute the owner's choice without sulking. Architects who sulk when overridden are the ones who lose the next project. Architects who refuse to recommend are the ones the owner stops trusting. The exam tests whether you understand the structure of a strong recommendation and the discipline of accepting the owner's authority to decide. 7 elements compose a strong pre-design recommendation document. 7 elements of a strong pre-design recommendation, and every one of them must be present or the document fails to do its job. An executive summary on the first page tells a busy executive the recommendation in 3 minutes, and most owners will only ever read that page, so the rest of the document supports the executive summary, not the other way around. Options analyzed lays out each alternative considered with documented pros and cons, so the reader understands what was actually compared. Evaluation criteria explains how the options were scored, what weights were applied, and what methodology was used. This section is what makes the analysis defensible in any future dispute. Comparative analysis presents the options side by side using consistent metrics, never with apples to oranges scoring. Risk assessment identifies the key threats for each option and the mitigation strategy for each threat. This is the section the lender or the board will scrutinize most. Recommended option states a clear professional opinion with rationale, not a hedge statement that refuses to commit. And next steps outlines what happens after the owner decides, including scope, schedule, and budget for the design phase. Miss any of these and the document is incomplete. There is one principle that overrides every other one on pre-design recommendations. The architect advises, analyzes, and recommends. The owner decides. That single principle is the one the ARE tests most often on pre-design questions, and architects who get it wrong fail those questions consistently. The principle applies to site selection. The architect can run the weighted scoring and recommend a site, but the owner makes the acquisition call. It applies to budget allocation. The architect can recommend how to split the program budget across building and site, but the owner decides what gets funded. It applies to phasing. The architect can recommend a sequence that minimizes operational disruption, but the owner decides which phase comes first. And it applies to virtually every other pre-design decision that involves trade-offs the owner has the right to make. The exam will present scenarios that try to tempt you toward answers where the architect makes the decision unilaterally. Those answers are wrong every time. The architect who exceeds advisory authority and unilaterally commits the owner to a path is the one who loses their license over a contract dispute, because the contract gave the architect advisory scope, not decisional scope. There is a specific scenario the exam tests where the owner picks a different option than the architect recommended. 5 things the architect must do when the owner chooses a different option than the one the architect recommended, and every one of them is the right professional response. First, document the owner's decision in writing, a meeting minute, an email summary, or a formal decision memo that the owner countersigns. The documentation protects the architect against future claims that the architect did not warn the owner. Second, document any concerns the architect has about the chosen option, in writing, professionally. Concerns about regulatory risk, budget exposure, or programmatic miss must be on the record before construction begins. Third, execute the owner's choice without sulking or undermining the decision in front of consultants or contractors. Architects who undermine the owner's decision in the room lose the client and lose the next project. Fourth, update the program document to reflect the chosen option, not the recommended one. The program is now what the owner decided, not what the architect recommended, and the design phase proceeds from that program. And fifth, do not relitigate the decision during design phase. The owner already decided, and second-guessing the call when problems emerge is the documented basis for the contract dispute that ends the relationship. Let me close with the 5 takeaways the exam keeps testing on pre-design recommendations. 5 takeaways from multi-criteria analysis and pre-design recommendations. 7 elements: executive summary, options analyzed, evaluation criteria, comparative analysis, risk assessment, recommended option, and next steps compose a strong recommendation, and none of the 7 is optional. The executive summary is what the owner will actually read, so the rest of the document supports the summary, not the other way around. The architect advises, analyzes, and recommends. The owner decides, and that principle applies to site selection, budget allocation, phasing strategy, and virtually every other pre-design call. When the owner chooses a different option than the one the architect recommended, the right professional response is to document the decision, document any concerns, execute the choice without sulking, and update the program to reflect what the owner decided. And never relitigate the decision during design phase. The owner already decided, and second-guessing the call when problems emerge ends the client relationship. Whose program is it when 3 stakeholders want incompatible things? That is the question Module 2 Advanced trained you to answer. Foundational programming gathered requirements. Advanced programming asks you to arbitrate between requirements that do not all fit. The hospital wants every patient room private, but the operating budget is sized for semi-private. The university wants 9 new buildings on a site that supports 6. 3 department heads want adjacency to the same atrium, and only one of them can have it. Choose badly under these collisions, and the project goes over budget on a foundation that cannot recover. The owner is sued by the board for fiduciary failure. The architect is sued for failing to surface the trade-offs, and the firm loses the entire client relationship. 5 subsections covered the advanced toolkit: campus and phased programming, cost and life cycle analysis, facility type programming, stakeholder prioritization with post-occupancy feedback, and multi-criteria site selection. The next 3 frames collapse them into the 3 threads the architect needs to arbitrate well: the strategic frame, the cost and value story, and the recommendation methods that turn arbitration into a board-ready decision. Start with the strategic frame, because every cost story and every recommendation in the next 2 frames depends on naming the right arbitration to begin with. 3 strategic frames name the real conflict the program has to arbitrate, and each one keeps the cost analysis from answering the wrong question. Campus and phased programming is the right frame when the project unfolds across years and parcels, rather than in one construction window. The architect documents not just the rooms, but the sequence in which they get built, the temporary uses that bridge between phases, and the connections that have to be designed today for buildings that get built 10 years from now. Mixed-use programming is the frame when multiple occupancies share a single building, residential over retail, office over hotel, lab over teaching, and the code separations, the structural transfers, the egress routes, and the mechanical zoning all have to be programmed together rather than handed off in sequence. Facility-type rules are the frame for projects with deep code-driven program requirements, healthcare with FGI guidelines and patient room sizing, education with classroom and corridor minimums, lab with engineered ventilation and chemical storage, residential with unit mix and accessibility distribution. The generalist architect who skips the facility-type background drives the program straight into a code-required redesign in design development. Naming the conflict correctly is necessary but not sufficient. Every advanced arbitration also rests on a cost and value story the owner can read. 3 methods tell the cost story when the owner asks why the cheaper option is not the right answer. Life cycle cost analysis tells the long story. First cost plus 30 years of operating, maintenance, and replacement cost. And the strategy that loses on first cost often wins on life cycle once energy, replacement, and remediation are folded in. The architect who can present an LCC analysis is the architect who wins the building envelope upgrade the owner would otherwise value engineer out. Cost benchmarking tells the contextual story. Dollar per square foot ranges by facility type and region. Healthcare sits in one band, education in another, market rate housing in a third. And the architect who can speak the benchmark fluently is the architect the owner trusts when the contractor's number arrives high. Value analysis tells the function over cost story. Function divided by cost is the formal method, and it asks which functions deliver the most program value per dollar and which can be reduced without compromising intent. Value analysis is the architect's defense when value engineering becomes a euphemism for stripping intent from the project after the owner stopped paying attention. The frame and the cost story turn into a recommendation only when documentation gives the owner's board something it can read and defend. 3 documentation methods turn arbitration into a recommendation the board can read and the owner can sign without second-guessing later. Multi-criteria site selection is the right method when multiple candidate sites are on the table and the owner weights criteria differently. Cost might be dominant for one owner, entitlement speed for another, neighborhood fit for a third. The matrix surfaces the trade-off transparently rather than letting the architect's favorite quietly win. Post-Occupancy Evaluation, the POE, is the method that closes the loop the foundational module opened. Yesterday's program decisions get evaluated against measured performance, occupant satisfaction, and operational cost, and that evidence feeds back into tomorrow's recommendation. Without the POE, the program is opinion in a loop. With it, programming becomes evidence-based design the board recognizes. And the documented trade-off memo is the artifact that holds the whole package together for board presentation. It surfaces what the owner is buying with each choice and what they are giving up. And it is the architect's protection when the board second-guesses the recommendation later. Skip the memo, and the architect is sued for ambiguity. Document it, and the recommendation survives the meeting. 5 takeaways close the advanced arc into the single posture the architect carries into every capital decision once licensed. Frame the conflict, tell the cost story, write the recommendation, and the 5 rules of advanced programming come into view as one practice posture. The first rule is that strategic frames sequence the program across years, occupancies, and facility types, rather than treating the program as a single point in time. Campus, phased, mixed use, and facility-specific are the lenses that turn a room list into a sequencing plan with the right shape for the project the owner is actually building. The second rule is that life cycle cost analysis defends design intent against first cost pressure. The strategy that loses on first cost often wins across 30 years once operating, maintenance, and replacement are folded in, and the architect who can show the LCC is the architect whose envelope upgrade survives value engineering. The third rule is that value analysis protects function under cost cutting. Function divided by cost is the formal method, and it is the architect's defense when value engineering becomes a euphemism for stripping intent from a project the owner stopped supervising. The fourth rule is that multi-criteria site selection separates owner-weighted recommendation from architect preference. The matrix lets the criteria the owner cares about drive the choice, and the documentation is what makes it survive board scrutiny. And the fifth rule, the one that holds the entire toolkit together, is that the documented trade-off memo turns analysis into a decision the board can defend publicly. Surface what the owner is buying with each choice and what they are giving up, and the recommendation rides on top of the memo rather than around it. Master this module, and your capital decision recommendations are the ones owners cite when the building outperforms its peers, and the board asks who saw the trade-offs clearly first.